All right, so we know that there's going to be a YY normal stress because in the Y direction we're going from a thickness of 0.2 to 0.198. We know there's going to be a ZZ. I said stress, I meant strain. We know there's going to be a ZZ strain because the length is going from 0.4 to 0.406. What about XX strain? There's not going to be because that thickness is staying the same. And then are there going to be any shear strains? Yeah, you're just looking for places where the two positive faces are going to change angles. So the angle between the positive Y face, this one, and the positive Z face, this one, change from 90 degrees to something bigger than 90. So what does that angle become? Yeah, 90.5. These two are, that has to be 180 degrees. So your shear strain, your engineering shear strain is just going to be pi over 2 minus, no, the other way around. No, I said it right. Pi over 2 minus 90.5 expressed in radians. Okay. So the YZ shear strain is going to be pi over 2 minus 90.5 times pi over 180. And you get a value of, negative 0.008727. Uh, 90.5 times pi over 180. Did you use 3.14 for pi or something?
Oh, you're talking about 90.5 times pi over 180?
Yeah.
That's 1.58.
Okay. I mean, as long as you're doing that stuff right, as long as you're putting the right stuff in the right order, I don't really care. But okay, I think that's probably round off error.
If you're using the TI-89, you change the mole, but you just have to put the degree on that 90.5 and they'll convert.
Okay. Okay.
What did you get, Noah?
I got negative 0.00904.
Like, did you punch in pi or did you use exact pi? I think that's probably the difference. Because, you know, this is going to be such a tiny number. Like, if you round off pi at all, then you know, the number is going to be significantly off. All right, so that's the engineering shear strain. And then the YY normal strain is going to be 0.198 minus 0.2 divided by 0.2. And so you get a value of negative 0.01. Final minus initial, yep. And then, and if you ever forget that, and a nuclear attack has ruined all the computer infrastructure and you can't look it up, just remember that you know that when something gets longer, the normal strain is positive, right? So that difference in the numerator has to be positive if the thing gets longer. You know what I mean?
Opposite with angles though, kind of then? So when angles get bigger, it's negative?
It is the opposite with angles, yeah. So positive for the shear strains is when the angle becomes more acute. Okay, so ZZ, we have 0.406 minus 0.4 divided by 0.4, and you get positive 0.015. And so the Voigt strain is equal to 0, negative 0.01, positive 0.015, and then YZ, so negative 008727, and then 0, 0. Okay, so now to get the stress, we know we're going to multiply this by either the stiffness matrix or the compliance matrix. How do you know which one? Well, I think the way to remember which one it is these numbers are little, right? We know the stresses are almost always going to be really big. The strains are almost always going to be really small. And so to multiply, if we're going to multiply a matrix times these small values and get big values, we're going to need a matrix full of big values. And if you look at the form of the stiffness and the compliance matrix, the stiffness is going to have big values and the compliance is going to have little ones. Okay, so we know we have to multiply this by the stiffness matrix. So that program in MATLAB that I just gave you, Mohammed, that was for the compliance matrix. So if we want, wait. Oh, actually, I gave you the stiffness matrix and called it compliance. So that's bad. Did you already send that to everyone?
Yeah.
Okay. Everything's backwards now. Okay. Well, we'll fix that. Yeah. But
I can
just change the name. And change the name of the function, too. You have to change the file and the function. I can do that after class. But anyways, the stiffness matrix is the one that's like E over 1 plus nu times 1 minus 2 nu. And then the matrix is 1 minus nu, nu, 0, 0, 0. And so then to get the Voigt stress, you're just going to go Voigt stress is equal to the stiffness matrix times that Voigt strain that you just calculated. And the vector that you should get is 3.0 times 10 to the 9th. 10 to the 8th. And these are all in pascals. And then negative 9.0 times 10 to the 8th. And then 2.1 times 10 to the 9th. And then negative 5.24 times 10 to the 8th. And then 0, 0. And notice that when we calculated the strains, there was no strain in the x direction, no normal strain in the x direction. But now, remember what I was saying before about the Poisson effect. The fact that there are strains in the other two directions means that that x direction doesn't want to stay the same thickness. And so you're going to have to apply a stress to it just to keep it from expanding or contracting. And so even though there's no strain in the x direction, you have to have a compressive stress acting on it in order to maintain that shape. Okay, so that's the Voigt stress. Then to get the stress tensor, you have to reformat that. So the stress tensor is like that. The YY is -9 times 10 to the 8th. The ZZ is 2.1 times 10 to the 9th. And then the only shear stress we have is the YZ. So that's here, -5.24 times 10 to the 8th. And it also has to be here because of symmetry. And everything else is zeros. Yeah.
Strain tensor.
Okay. All right, so once you have this, how do you come up with the principal stresses? Yeah, so all you're trying to do now is find the eigenvalues of the stress tensor, and that'll give you the principal stresses. So like on a TI 90, TI 89, I think it's called like this, eigenval of, put in that matrix. And you'll get the values 2.19 times 10 to the 9th, -9.89 times 10 to the 8th, and 3.0 times 10 to the 8th. And then the last thing is, how do you come up with the max shear stress?
The two largest ones that you add together and divide by?
Okay, yeah, it's the two that are the farthest apart. Well, is that true? Yeah, I mean, you want to cover as much range as possible. So, like, if you have a -1, you're going to take the biggest positive one and the -1. So in this case, the biggest one is 2.19 times 10 to the 9th. The smallest one is -9.89 times 10 to the 8th. So the max shear stress is going to be 2.19 times 10 to the 9th minus that negative. So remember, you're not adding these, you're subtracting them. And then divide by 2. And I think you get a value of 1.59 times 10 to the 9th. And so if you have a material that you expect to fail in shear, then you'd want to compare this value to what the allowable shear stress is.
Those eigenvalue stresses, are those like the XX, YY, and ZZ?
It doesn't actually matter. You could put any one of they're the 3 normal stresses, but you could organize them in any possible way, and that's correct, It's just, like, if you reorder those, it's basically just switching your coordinate system to different orientations.
Comes with an angle.
You could come up with an angle, but we're not worried about that. It's always 45. It's always 45 degrees off from that. So when you get your principal stresses, there are 2 of them you use to calculate to calculate the max shear stress. And the max shear stress is always going to be oriented 45 degrees in the plane of those two. Okay. Any other questions about that? Okay, well, let's stop there. So this is the kind of thing that's going to be on the test. So I would recommend just figure out how you're going to do those calculations, get smooth at it. There's not going to be any like surprise stuff on the test. Just get comfortable doing the kind of stuff that's on those practice problems.